In this video, let's solve question 7. In this question, we want to prove an inequality by mathematical induction. So the equality is the summation of r from 1 to n of r over r plus 1 factorial is equal to 1 minus 1 over n plus 1 factorial. For all integers, n is greater than or equal to 1. So let's call this statement P of n first. So let P of n be the statement, the summation r from 1 to n r over r plus 1 factorial is equal to 1 minus 1 over n plus 1 factorial for all integers n which is greater than or equal to 1. Okay. So the first step of this of mathematical induction is that we want to prove P of 1 is true. So first, we prove P of 1 is true. Okay, so when n is 1, the left-hand side of the statement P of 1 is going to be the summation. So when n is 1, the summation on the left should be r equal to r from 1 to 1 r over r plus 1 factorial, and it is just 1 over 2 factorial, which is 1/2. And also the right hand side of this statement is 1 minus 1 over n plus 1 factorial is equal to 1 minus 1 over 2 factorial, which is 1 minus 1/2, so it's 1/2. So we see that the left-hand side is equal to the right-hand side in this case. Okay. So this means that the left-hand side is equal to the right-hand side of P of 1. Okay. Next, we want to show that we want to assume that P of n is true for some n is greater than for some integer n which is greater than 1, and then prove that P of n plus 1 is also true. So our next goal is to first assume P of n is true for some n greater than 1, and we claim, or we want to show, that P of n plus 1 is also true. Okay. So let's look at the left-hand side of P of n plus 1. So the left-hand side of P of n plus 1 is the summation r from 1 to n plus 1 of r over r plus 1 factorial. Okay, so usually we'll call this assumption the induction hypothesis. So it is called the induction hypothesis, and I write IH stand for the induction hypothesis. Okay, so now let's back to the summation here. So it is equal to the summation r from 1 to n of r over r plus 1 factorial plus the last term, which is when r is equal when r is equal to n plus 1. So the last term is n plus 1 over n plus 2 factorial. The reason why I decompose this summation is because that we can use because that we can apply the induction hypothesis now to the first term. So after applying the induction hypothesis, the first term is going to be 1 minus 1 over n plus 1 factorial, and then plus the last term, which is n plus 1 over n plus 2 factorial. Okay. So let's combine the last two terms. So it's going to be 1 minus. First, we find out the common denominator for the last two terms. So I think the n plus 2 factorial will be a good choice. So in order to have the common denominator, let's multiply n plus 2 to the denominator and the numerator of the second term. So we multiply n plus 2 on the both up and down. Then we will get n plus 2 over n plus 2 factorial for the second term, and then plus the last term. We don't have to change the last term because the denominator in the last term is already n plus 2 factorial. Okay. And then we combine the last two terms to get 1 minus. Okay. So 1 minus. So it's going to be 1 minus. Here should be n plus 2 minus n plus 1 over n plus 2 factorial. Okay, so it is 1 minus n plus 2 factorial and 1 over n plus 2 factorial, which is equal to the right hand side of p of n plus 1. So it is equal to the right hand side of p of n plus 1. So this completes the proof of the second step, and thus completes the proof for the whole question.